foundations. I thought this is no longer strange to you, or this is not new to you because we discussed already in our subject before in construction technology about pile foundation. But then it's very important for this unit for you to make calculation. Okay, before it's only a theoretical, discussion, only discussion about pile foundation or about foundations. Now I'm going to discuss with you first what is pile foundation, and then some important calculation. Okay, so here we are going to learn about the different types of pile, and then installation. How are you going to install it or to construct in the site? Then you will also learn how to determine the bearing capacity of a pile, which is the one very important, as I told you, necessary for your assignment number 2. My voice is clear, right?
Yeah.
Okay. So hey, we're already here. Can you see the slide?
Yes, sir.
Okay, very good. Pile foundation. These are long, slender members which transfer the load to soil of high bearing capacity beneath shallower soils of lower bearing capacity. As we discussed already before, even in previous classes, units, we have in construction, civil engineering, we discuss about foundations, substructures. We all know that we need pile if we have deep foundations, okay? Because this pile could reach the very deep, location of the hard or the strong soil. So just like locations like in Seth or in Jaffer or some other areas beneath the sea, or some soil which are not strong. Piles may be made from concrete. It could be concrete, could be steel or timber. In some other countries, they're using timber if that's only small or not big projects or not big building. They are installed by driving, drilling, or by jacking. There must be a pile cap at the top. As you can see, just like a beam at the top of the pile. Have you seen pile already? Hello. Have you seen pile?
Yes.
Drive. Okay, very good. So, I'm on number 4. Are you with me? Slide number 4.
Yes.
So, piles may be characterized by their method of construction. So, as far as I remember, during our last unit in construction technology, we discussed different piles. So, there are this following type. First, driven or displacement piles. There is also driven, which is cast in situ piles. There is also board piles, continuous flight auger, I should say, or CFA, and then raking piles. So we discuss this one by one. As you can see here, this one is driven displacement piles. Okay, these are precast units. Usually, for piles, we always think about precast. Okay, as you can see in the pictures, this one is rectangular and shape, but there are also shaped circular. As far as I know, with my experience, when I was in Oman constructing dry dock. So you also have your dry dock, ASRI. We are using PHC, high strength concrete pile. Okay, pile with high strength concrete with tendons. Okay? They are also precast. So it's being driven. Okay, just like as you can see in the picture with my cursor, it's being driven with a jack. Okay, with a weight, with a hammer, driving on the soil. So as you can see further, driving up piles, the location by which the soil is very soft, right? Because if it is not soft, obviously you're not going to use pile. You may just use pad or isolated footing, or maybe a mat footing if it's really not a good soil or not a very strong soil. But if the bearing capacity, strength of the soil is very low or very weak, then you are going to use pile foundation. So you have here the picture pile driver, and then there is a rapid installation. This rapid installation because according to the need of the soil, it could be the spacing could be very close. I'm already in slide number 7. Are you with me?
Yes.
Okay.
Yes.
So the piles could be very close. It could be some kind of spacing apart, depending on the load of the structure. As far as I know, yeah, as I told you when I was in Oman, the pile is carrying a crane. Okay, a crane. So obviously the spacing is very close. Okay, 1.5, 1 meter. If it's 2 meters, the size of the pile will be bigger also. Okay, so that would depend if on the type of the structure. Because if your load is only for house, let's say for residential house, not that necessary. Maybe in one area of a house you only need 4, maybe 5. But if you're building high-rise, 20-story, 30-story, just like in the Wyndham Hotel or the Four Seasons Hotel in Byron Bay, so that could be a very close one. The spacing of the piles might be very close. So there is also the other one, cast in situ. You know cast in situ, right? Right? What is cast in situ?
The casted on site.
And the
Yeah,
site.
very good. It's in place. So, for example, here you have 25 thick heavy steel tube. So there's a casement, a casing, or a form made of steel, and then you put the concrete inside. Okay. So depending on the type of pile, just like mostly for board piles, okay, you have a boring, but this is just a hollow circular case. Okay, so as I said earlier about board piles, you need to have a drilling, no? Just like a boring machine or boring equipment. Okay, when you bore or when you drill, you use just like a driller. Okay, so you make a hole out of a drilling equipment. So during drilling, the sides of the borehole are supported to prevent the soil from collapsing. Because if there is no support, once you drill, the soil will get in. Okay, so the purpose of the forms will prevent from the soil to get inside. So there will be temporary sections of steel cylindrical casing, so together drilling to support the sides of the soil. As the drilling progresses, as you can see in the slides, the soil is removed from within the casing and brought to the surface. So that's the time now that you can put the reinforcement and the necessary putting of concrete. Just like this one, you can see the steps. Once you drill, then you go to the reinforcement, okay? Put the reinforcement and then later with the concrete. Once the full depth of the borehole has been reached, the casing is gradually withdrawn, so the case will be withdrawn. The reinforcement cage is placed, and the concrete which forms the pile is pumped into borehole. Usually this is done, I have observed, I don't have personal experience with this, but my observation during site visits, for bridges, usually for bridges, in the Philippines, for bridges, they use borehole, okay? Not, of course, not a very big or wide type of bridge along the ocean. Maybe it could only be a river, stream. So these are the equipment, okay, in use for boring. I think there is also like this here in Bahrain. Have you seen like this here in Bahrain?
Yeah.
Yeah, I think because this one is familiar.
I think for that SAR interchange, also.
Where's that one?
SAR interchange. That
Okay.
bridge.
Yeah, it's very common for. As what I have noticed, very common is the precast type of precast of pile, and then this board pile are most common. There is also, as you can see, this enlarged base piles. This is just similar to the previous kind of pile that we discussed, but with a specific purpose of this one. And stiff cohesive soil. What is cohesive soils? What kind of soil is that? What are cohesive soils? Can you give example of cohesive soil?
Same
What
the
type?
clay.
Huh?
Same the clay. Weak
Same with what kind of
clay.
soil? Clay. Yeah, very good. It's clay. It's the opposite of the granular. Cohesive is the opposite of granular. So, example of granular is what? Sand or gravel. Okay, they are granular soils. Cohesive, these are clay. Okay, just clay is a very good example. Okay, so you also have here this continuous flight auger, CFA. Okay, with hollow steam is used to create the borehole. Similar also to boring. What's the difference? The sides of the borehole are supported by the soil and the flights of the auger, and so on. No casing is required. So there's no casing. Okay? Once required depth reached, concrete pumped down the hollow stem, and the auger is steadily withdrawn. So as you can see here, the steel reinforcement is placed under the auger is clear of the borehole. CFA piles are particularly suitable in poor ground conditions where they can be installed with minimum vibration. So it would depend on the type of the soil. Very poor ground conditions. There are some locations of the project by which you have to avoid vibrations, because when you're doing boring, there's really vibration. Or if you're going to use pile made of precast, just driving or jacking the pile makes vibration on the ground. And if you have a very poor condition, then that would affect somehow the adjacent building. So what you need to do is to look for other type of piles by which CFA is very appropriate. There are also raking piles, as you can see here. Okay? Raking pile, it is just like a diagonal type to support to support the pile cap. What is this raking piles? Are piles that are installed at an inclined angle, or diagonal, inclined to the vertical. They are used to provide resistance against applied horizontal forces where vertical piles would be inadequate in resisting this. Where can you find structures by which there is a possible movement in horizontal direction? What do you think? What structure which possibly could move in horizontal direction? What do you think? Any idea?
Again,
What you-
teacher.
For what?
Can you repeat the question? Because
Okay, the question, because rigging files is installed in diagonal, okay, inclined. So the purpose of which is to support the structure from a possible horizontal movement. So which do you think, or do you have any idea of a certain structure that could possibly move in a horizontal direction that needs to have a raking pile? Hmm?
maybe in the hilly area, maybe
What's that?
hilly area, like not plain area.
Not plain area, or yeah, possibly not plain area. Can do that if that one is somewhat sloping. What do you mean? You mean like that?
Yeah.
Yeah, because yeah, that's good. Because for example, one side is a made of a sloping ground that could possibly be an effect. The effect could possibly lateral movement, just like erosion or landslide. Yeah, that could be correct. But another one is there's also the presence of some horizontal movement, just like possible earthquake. It's also one reason. And then if your structure itself could be resisting horizontal movement. For example, it may be used for railway or a craneway. You know, there is a crane moving in sideways direction, so possibly there is a force in its horizontal direction. If you are going to visit some dry dock or some pier or some seaport, there are crane, right? That could the purpose of the crane is to transport or to bring the what's this materials from the ship going to the factory or the warehouse. So they're using crane. So this crane is just like with a roller running over the railway. The railway is on the top of the pile cap. So the pile cap could be supported by a raking pile. Okay, so that's one example also. Aside from what you said, Mr. Sohaib, that it could possibly in a certain location, just like a sloping area by which there is a possible movement in horizontal direction. Okay, it's good. Then the classification of piles. In terms of pile design, if you're going to design now the piles, they're best classified by the way they act in service. So there's what we call end bearing, friction, and combination. What's your understanding about this first end bearing? Any one of you, Mr. Suhaib, how do you understand this end bearing?
It is for the pile is extended until the hard strata.
Yeah, that's good. So there is the end reaction or end bearing or the end capacity of the bearing between the end of the pile and then the hard strata. So it penetrates on the hard strata. So there is a bearing. When you say bearing, it's a contact between two bodies. It's the contact between the end of the pile and then the hard part of the soil or the strata. How about friction? Ms. Fatima,
Yes, teacher.
how about friction? How do you understand that friction? Letter B.
I don't know.
You don't know. Miss Zainab, what's your understanding about that letter B, friction?
It is not too much deep.
Okay. Not too much deep, by which your resistance of your pile is only at the sides of the pile. You know, friction is a resisting force, okay, along the movement of a certain body. So the direction of the friction is at the side of the pile, while end bearing is at the end, the area opposing the pile. Later, in our calculation, you can see the difference, okay? But in the actual one, mostly it is between soft, it is between end and then friction. There's a resisting force at the sides of the pile, and then there's also a resisting force at the end of the pile. If you can see here, here is the, no, you can see here. This one is the location of the, you can see the, can you see that arrow? Can you see that arrow?
Yes.
That's end bearing. It is at the bottom of the pile. But when you have friction, it's at the side. See? You can see the difference? I made an arrow at the sides of the pile. But if it's combination, you have here at the side, and then you have also here at the bottom. Okay, that's the combination. You see the difference?
Yes.
Okay, so let's continue. So in pile design, okay, you're going to calculate the bearing capacity. Okay? The pile design or the design of pile foundation involves checking that the ground resistance of the soil supporting the pile is adequate to resist the forces being placed on the pile and transferred to the soil. What does it mean? Anyone? What's the meaning of this statement?
Like it
Huh?
is for checking the resistance of the ground. It
Yeah.
can bear the pile or no.
If it can.
It can bear the load of that pile like that.
Okay. Almost. Okay. But I'll make this very clear. Okay. Our pile, the pile is to carry a certain load from the building, right? And then the pile has also capacity. The pile, the pile capacity should be bigger than the load of the building. Let's say if the building is 1,000 kilonewton of the load, the pile capacity should be greater than 1,000. It should be 1,001, 1,002 like that. Okay. Then the soil should also be greater than that of the load of the building or the load or the capacity of the pile itself. At least it's greater 1,000 or greater than 1,001, 1,002. Because if your soil, even if the pile carries, has the, even if the pile has the capacity to carry the load of the building, and then the soil is weak, then the building will still collapse. The soil should have the resistance. The strength of the soil should be adequate to carry the load of the building being carried by the pile, which is being transferred to the soil. Am I cleared? Is it clear? Huh?
Yes.
So, meaning, you have to compute the resistance, okay? The ultimate bearing capacity, QU, is the sum of the base resistance and the shaft resistance. So, you have the base resistance, QB, you can see on my cursor, which is at the bottom of the pile, and then QS, which is at the sides of the pile. So, you see the difference? QS, or the skin, which is about the friction, and then QB, which is about the end bearing. The total ultimate bearing capacity is equal to the end bearing and then the shaft or the base resistance, QB, and then the shaft resistance, which is at the side. But you have to take note that different types of soil has its different formulas as well. Okay? But here, what you need to remember here is just the formula. When you have cohesive soil, let us say your location of your project has a soil, has a clay type of soil. So what is that type of soil? It's cohesive. So you're going to use the cohesive soil formula. If the type of the soil is uh, sand or gravel, then it's a granular type of soil. Okay? So you're going to use the formula for granular soil. So first, cohesive soil. As I said earlier, that the ultimate bearing capacity is equal to end or the bearing resistance, the end resistance, which is QB, or the base resistance, and then the skin resistance. The base resistance is just equal to CB times MC times AB. What is CB? This is the undisturbed undrained shear strength at the base of the pile. These are the shear strength of the soil, which is taken from soil investigation. Okay, you get sample of the soil, you test it in the laboratory, then you get the strength of the soil. That's it. In the problem, it's given. Okay, AB, the cross-sectional area of the base of the pile. So how do you compute the cross-sectional area of the base of the pile? Any idea? Any idea? What is the cross-sectional area of the base of the pile? Let's say the pile is circular in shape or circle.
Pi r square.
Huh?
Pi
Pi
r
r squared. Yes, very good. Pi r squared or pi d squared over 4. It's up to you to use it. Okay? MC is usually taken as 9. Okay? It's 9. So you already have QB. For QS, or the resistance in the skin or in the shaft, is equal to CA. Again, CA is just the underage shear strength along the pile. It's also given. It's taken from the laboratory testing, okay, from soil investigation. If you are going to solve that one, the problem, it's given. AS is the surface area of the embedded length of the pile. So how do you compute the surface area of the pile? The shaft or the side. What's the area of the side? If it is circular, what's the area of the side of the pile?
Pi r square, لا teacher.
No. Pi r squared is the base.
Okay.
How about at the side? How about at the side? Example,
into
if
length.
you come again,
Pi r square into the length.
not pi r squared. See, this is the pile. If you are going to look at what's this? What is the cross section is circle. Okay. What is the total circumference of the circle? What is the circumference of the circle? Huh? Circumference or the perimeter. C is equal to what? You forgot the formula?
4 pi over 180.
4 pi over 180.
Teacher, you want the area of the cylinder?
No, the area of the sides, okay? Only the sides, not the area of the cylinder. The area of the base, the area of this one is pi r squared, right? Area of this one is pi r squared. But the circumference, look at my arrow, the circumference, or when you're going to travel at the sides, the total length, circular length. You forgot the formula? Pi, right, just pi times d, or the other one is 2 pi
By R.
r, or see? It's the circumference. If you have the circumference, and then you have
The length you can multiply.
You
by
want
that.
to find the radius, right, teacher?
no, radius is given. We need to find the area of these sides. Here, all of these sides.
Right.
All of these sides.
نجمع أطوالهم لا.
All of these sides.
بالمحيط.
Okay, I'll show you. If this one is the total length, we call it L, then the area of the skin or the area of the
2
shaft
by R plus L.
times, not plus, right?
Okay, times L.
Area of the shaft is pi d or 2 pi r times
L.
L. Okay? So that is AS.
Okay.
Understand? Easy. Every circle, you know it already, pi r squared or pi d squared over 4. So, for cohesive soil, QS. But wait, okay? Here. CA. Okay. CA, as I told you, it's taken from, but the formula specific for formula of the shaft is equal to CA. Ideally, CA should be determined from a pilot test, but since this is not always possible, so CA is equal to, what's this? alpha, which is the addition factor ranging between 0.3 and 1. In the problem, if you have a problem, it's given, okay? In the design or in your assignment, I will give it to you from 0.3 to 1. CU, it is the average undisturbed undrained shear strength along the pile. Average, how do you compute the average? If at the top, let us say, at the top the shear strength is 30, at the bottom the shear strength is 60, how do you get the average of 30 and 60?
Again, teacher.
How do you get the average of 30 and 60? Let us say
30 plus 60 over 2.
Very good. Okay. So if, for example, this is your file, here at the top is the CU is equal to 30, and then here at the bottom, at a certain distance, CU is equal to 60, example, you get the average. CU with a line at the top, meaning average undisturbed undrained shear strength. It's just the average. 30 plus 60 divided 2 is the average. Okay? So you have this alpha, which is equal to 0.3 or 1. Average CU, which is 30 plus 60 over 2. Then AS, the area, which is earlier, I've already given with you. Then you can compute now QS, or the shaft resistance. You already have the end resistance or the base resistance, then you can compute the total ultimate bearing capacity. Okay? That is only for cohesive soil. What if your location of your project is a gravel type of soil or a sand? So it's no longer cohesive, meaning it's granular. If it is granular, you are going to use this. Okay? QB, bearing capacity at the base, is equal to YZ times NQ times AB. And YZ, it is the effective overburden pressure at the base of the pile. Y, the unit weight of the soil. It's also given. Z is the height or the depth from a specific location or from the ground to the end of the base. Okay. NQ, it's also given. Okay. AB, area of the base, pi r squared. Okay. How about in the shaft or the skin? Fs times As. Fs, again, it is the average skin friction along the pile. Okay. At the top is 30. And 60 maybe at the bottom. The average is 30 plus 60 divided 2. Okay. AS, the area of the embedded length of the pile. It is just the area of the sides or the shaft. Sides of the shaft, which is the circumference times length. It's already, I've given to you earlier this one. Okay. The area of the shaft is this one. Okay. Pi times D times L, or 2 pi times R times L, depending on your preference. Okay, but Fs is also equal to this. Okay, Fs is given to be equal to Ks YZ tangent, as this delta. Ks is also given. Okay, these are taken, or this value is taken from the laboratory. In the exam or in the assignment, it's already given. YZ with the line at the top is average. Okay, average effective overburden pressure. In the example, you will see how it's being computed. And then you have delta, is the angle of friction between the pile and the soil. It is usually given. Okay. So both Ks and alpha and the delta depend on the density of the granular soil. So if it is concrete, if the pile is concrete, if it's timber, it will vary. But it's already given in the problem. For a concrete pile, if you, for example, if your pile is made of concrete, then you can use 0.75, this phi. What is phi? The angle of friction. Kb may be taken as 1 for loose soil and 2 for dense soil. In the problem, it's identified if the soil is loose or if the soil is dense. Usually dense are clay. Loose usually are soil which are granular. Okay. So example, I'm already on slide 22. Are you with me?
Yes, teacher.
Okay, this one is just easy. Okay. It is proposed to install a pile diameter. The diameter is 300 millimeter. The length is 6 meters into a normally consolidated clay. This is clay. So what type of soil is this? Cohesive or granular?
Cohesive.
Very good. Very good. Laboratory results from a ground investigation have shown the clay to have an average average undrained shear strength of 100 kilopascal. Average meaning that is Cu with a line at the top. See? That's for the skin, for the shaft, or for the side. Over the depth from 0 to 6, the average undrained shear strength is 100 kilopascal. Meaning, if this one is 0 at the ground, then 6 meters below, the average undrained shear strength is 100 kilopascal. Then the undrained shear strength of 160 kilopascal at the depth of 6 meters, meaning at the base, here at the base, is already 160. So first, if you're going to calculate the base resistance, the formula is this one, right? I already introduced to you in the earlier slides. For cohesive type of soil, this is CB plus, or CB times NC times AB. CB is the undrained shear strength at the base, which is equal to 160. Then NC is given, 9. Then area of the base, pi r squared or pi d squared over 4. It's the same, okay? So you got her the base resistance. How about the shaft resistance? The formula is alpha times Cu, which has a line at the top, meaning average undrained shear strength. It's given to be 100 kilopascal. If it's not given, for example, this one is 40, this one is 160, you have to get the average of 40 and 160, okay? But this one is already given, so you just have to substitute. Area of the shaft, pi d, or 2 pi r, pi d. Diameter is 400 millimeter or 0.4. Pi d times L. Then you get the value of the shaft resistance. So the ultimate bearing capacity or the resistance is just the base resistance plus the shaft resistance. Substitute it, then you get the ultimate bearing capacity. Is it clear?
Yes,
Easy.
teacher, clear.
Okay, next slide. This one is a little bit complicated, but still, it's just procedural, easy. A 500 millimeter diameter bored concrete pile. So this pile is 500 millimeter. Using boring or bored pile. To be formed in a soil profiling comprising 3-meter loose granular fill material overlying 4-meter dense gravel. So there is a 3-meter loose granular fill above the overlying or above the dense gravel, which is 4-meter depth. Okay? So the 3-meter at the top is loose granular. The 4-meter below it is dense gravel. And then overlying a deep deposit of glacial clay. So after that one is already clay. Okay? So first 3 meters granular fill. The second is dense gravel. The rest is already a clay. So these are the ground conditions or the properties. Okay? Y is 20 kilonewton per cubic meter, or the unit weight. The granular, this phi, angle of friction, which is 30 degrees. Ks is equal to 1 because it's loose. Okay. Now when it's dense, it's 2. You can see here. If it's not given, you should have to remember it. When it's dense, it's 2. Ks is 2. When it's loose, Ks is 1. Okay, so these are the values for the dense gravel. Now for the glacial clay, Y is 20, the same. Cu at 7 meters. Where's 7 meters? This one is 7 meters. 3 plus 4, 7 meters. Cu here is 120. Cu at 8 meters, somewhere here, is 145. And then Cu, or undrained shear strength, at 11 meters depth, somewhere here, is already 220. Adhesion factor, or alpha, is 0.6. MC is 9. The question is here. Compute the bearing capacity. First, when the embedded length is 8 meters, so when the pile is just up to 8 meters, what is the bearing capacity? Now, when the embedded length is up to here, 11 meters, what is the bearing capacity? So first, you compute first for the embedded length at 8 meters. The letter B at 11 meters. So here, first, you have here the shaft resistance. The formula is AS, KS, YZ tangent alpha. YZ is the average. What is the area of the shaft? For the fill only, because there is a difference in properties between the fill, the granular fill, and the dense gravel. For the fill, pi d or 2 pi r, what is the length? Only 3 meters for the fill. Very good. Okay. KS, since this one is loose soil, it's 1. Different from the dense, right? I thought you could understand with this arrow. Here, what is this? YZ with a line at the above, or the average.
The
Okay?
average.
Yeah. 20 times 3 over 2. Because here,
Teacher, why
Here-
the average multiply, not addition?
no, it's the distance. You have to multiply by the distance. Okay? By the height.
Oh,
Okay. I can put it at the here to make it what's the kilonewton is cubic meter. Okay, you still have to multiply by the height. Okay, you can multiply first there 20 times 3. Okay, but since here at the top it's 0, it is just like 0 plus YZ here. YZ. Y is 20. Z is 3. Z is 3 meters. But here, it's 0 from the
0.
top. Yeah? 0 plus YZ. YZ here is 20 times 3. 20 times 3. Y is 20, Z is 3. Then you divide it by 2. Okay? I can show it later here. The value of this one is 60. This one, right? Okay. Let's continue first at the top. Times tangent alpha. What is alpha? We use 0.75 times 30. Why is it 0.75? I think I have.
The pile, it's pink of.
I mentioned it already earlier, but it's 0.75. Okay,
Yes.
in the slide. Phi 30 is phi, right? 30 degrees. It's given 30 degrees. Okay, 30 degrees. You use 0.75. Or the type of the pile, because of that it's the type of the pile. You are going to use 0.75 of the 30. I think it's I mentioned it here with you. See this one. For concrete pile, delta may be taken as 0.75 for concrete pile. Okay, because that is concrete pile. Okay. Oh, let's continue. So you have this one. So you can compute the shaft resistance only for fill. But then you also need to compute the shaft resistance for gravel. Dense gravel. Again, the area of the shaft, pi, 0.5. L is the 4 meter. Okay? 4 meter height. Times Ks is the dense soil. K is for dense soil. Then the average. Here is already 60, right? That's why this is 60. At 3 meters, that is 60. Okay? At 4 meters, that is, what's this one? It's given to be 21. See this one? 21. The Y for gravel is 21. So it's 21 times 4. YZ here is 21 times 4. Okay? Over 2. then you add the 60. Okay? Because this one is already with divide 2. Here you just have to divide by 2. Okay? Is it understood?
Not too much.
Not too much. Okay. Okay. It is just like here. Okay. I'll make here more. Here it is already, it's YZ here is 20 times 3. Okay? 20 times 3 is
60.
60. Then here, you can also have here 21 times 4. Here, 21 times 4. Oh, no. Here is 21 times 4. What's 21 times 4? 44. So you can, it is just the same as 60 plus 44 over
21
2.
times 4, 84.
Oh, 84, I'm sorry, 84. It is just like 60 plus 84 divided 2. Okay? You can do like that. Okay? And just continue with, anyway, times tangent. Since this one is concrete file, 0.75 of angle of friction. Then you can get this one. Okay, we are only here up to here. Okay, now we have clay also. So we are finished with this one. We just finished with this one up to 8 meters because the first question we are asked only up to 8 meters, right? So Q is for the 8 meters up to here. So we are just have to compute from 7 to 8 meters. Okay, what is the? This one is already for what? Clay, right? The first one is granular fill and gravel. What is gravel? It's granular. This one is cohesive. Okay? So for cohesion, the formula is this one. This one is for granular soil. For cohesive soil, the formula is this one. Alpha. What is alpha? It's given 0.6. It's here. Okay? The average. The average is already given 120 and 145 divided 2. Right? 120 and 145. Well, it's 120. 120 at 7 meters. 145 at 8 meters. It's already given 120 and 145. Divide 2 to make it average. Area of the skin or on the shaft, pi d times, why is it only 1? What do you think? Why it's only the L is 1?
Again, teacher?
Why L is only 1 here? Pi d L. The area of the...
Because 8 plus 7.
Yeah, it's between 8 and 7 years, only 1. Before there is 4, there is 3. Okay, very good. So once we computed this, yeah, very good. So once we computed this one, we already have the sides. Okay, now the base resistance. It's by this formula, CB NC times AB. CB is 145. It's already given here. Okay, 145 at 8 meters. See, at 8, 145. NC is given 9. AB, the end area, pi d squared over 4 or 2 pi squared. You have this. So you just add. At 8 meters, 256 plus this calculated before. At 11 meters, you will again calculate for the clay. Because before we only calculated for the clay up to 8 meters. For 11 meters, the difference is only instead of here 1, it became 4, right? Why it's 4? Because it's between the 7 and 11 meter depth. Between 7 and 11 meter, there is a total of 4 meter. Okay? The same calculation here, but we changed just from 1 to 4. And the base, CB is 220 and C, it's, it changes with CB 220 because before it's 145. Now it's 220. So just with the formula. So at 8 meters, you have this value of the bearing capacity. At 11 meters, this is the value of the bearing capacity. What's that? Any question?
No, teacher.
Okay. Visit Moodle, okay? There is formative activity.
Teacher,
The
the
exam,
activity is similar to the first example or second example?
just check it there. If you don't know, I will share with you the solution, okay? How you are going to do it. Just, it's easy, only easy, huh? This one is a little bit difficult. Example is just similar, easier. Okay, you try to answer then upload it. Okay, I will give you. We have remaining minutes, 40 or 50 minutes. Try it now and then take a picture, upload it in Moodle.
Okay.
If you're gonna find, if you're gonna upload it in yourself, and better to open your laptop. Okay. Any more questions?
No.
Okay, I will stop the
Teacher,
recording.
teacher,